Okay, good morning. Today we will continue to introduce the basic related to a semiconductor a device. Especially today we move on to the crystal structure, and also the next chapter we will move on to the quantum mechanics, which will be the main focus. We will only introduce a part of the quantum mechanics that's which is enough for us for the semiconductor physics analysis. Okay, so last week we actually have been mentioned that when we talk about the semiconductor device, there's which is critical part is about the formation of the junction. So we have the 4 types of the different junctions that we will mainly focus on in these classes. And then actually these 4 types of the junctions already include every cases that you will face in our semiconductor device. So the first one is a metal semiconductor. So when we talk about metal semiconductor, the most important part is to understand the transport and then the physics between the metal and semiconductor junction. And the second part is we consider to have the 2 different doping type of the semiconductor that we put together. So in the end, we can form this PN junction, which is also very crucial. That in the end will lead into a very important device that we call the PN diode. And also we can consider that we have the 2 different materials that can be connected with each other. So sometimes we have the 3,5 compound on silicon, or we have the other different material on the silicon. So in this case, the junction between these 2 semiconductors are also very important. And the last one is that we will talk about the junction between the metal and then the insulator and then the semiconductor. So this metal oxide semiconductor, which is very important in the end to understand the MOSFET characteristics. So this is what we have been mentioned last time, that regarding for the metal semiconductor, we have the 3 different type of the MS junction. One is a Schottky contact, another one is the ohmic contact, and the last one is the metal semiconductor transistor, and usually we call it a MOSFET. And regarding to the P and N type of semiconductors that are being connected with each other. So basically we have the PN diode, and the next one is we can have the bipolar junction transistor, which is shown in the schematic like here. So we have a PNP or NPN together, and we also have the what we call the junction FET, what we call the JFET. So the idea is that we will use N-type substrate, and then we try to, in most of the case, we use implantation to dope the P-type region, so we can form the PN junction in this region. So we can also use the operation of the PN junction to control this transistor. So that's we call as a junction FET. And the last one is that we can consider the 4 type of the junction that we will use for the PN. So that's we call as a thyristor. And last week we also mentioned that it is possible to have the 2 different semiconductor materials that are being connected with each other. So this is usually we call as a heterojunction here. So one of the most famous example is, for example, the LED is based on the heterojunction, and also the laser diode, and also the HBT, which is a heterojunction bipolar transistor, and last one is a high electron mobility transistor here. So in this slide, I use the example of the hand structure, which is the bottom side is a typical 3,5. That's we use gallium nitride, and on top of gallium nitride, we try to have another similar to the 3,5, but just add a little bit aluminum content. In the end, we can form the aluminum gallium nitride. So by growing the aluminum gallium nitride on top of the gallium nitride here, so we actually are able to have the structure that we call the gallium nitride hand structure. And this hand structure is featured with very important. We have the two-dimensional electron gas, which is 2D EG, will be formed between the L GaN and GaN, and that can give us a very high electron mobility. So that's the ideas behind that, how the GaN hand works. Okay, so the last one is a metal oxide junction here. So the first device that based on the metal oxide junction, which is the MOS capacitance. And then the second one is a MOSFET. So if you look at the schematic of the MOSFET, where we have been draw already here. So this, if you look at this, is a full structure for MOSFET. It's basically, this is a MOSFET is combined with MOS capacitors. This is MOS capacitor, plus we have a PN junction here. So that means once we understand the MOS capacitors and PN junction, and basically we can fully understand the operation of our MOSFET. So the MOSFET basically combines MOS capacitor and the PN junction. So that's why in most of the semiconductor physics and device textbook is always, we will talk about the PN junction first, and later we talk about the MOS capacitors. And once we have the knowledge to understand the PN junction and MOS capacitors, and then we will introduce MOSFET in the end. Okay, related to the fundamental series, so we have several important fundamental series that help us to understand the semiconductor device. And then the first one, which is quantum mechanics. So to understand the quantum mechanics, we have to use this Schrödinger's wave equation. And then by using the quantum mechanics, we can also understand the Venn diagram theory. So these two we will explain in the details later. And the second one is the carrier transport. So in here, for the carrier transport, that means we try to understand the electrons and holes transport in the solid state material here. So the first one, we will try to develop the bipolar transport equation. The bipolar transport, that means we consider the carriers of electrons and holes together. So we try to develop an equation that be able to describe the electron and holes transport in the one piece of the solid state material. And also we have to consider the different mechanism related to, for example, once we have a different doping concentration, so we will have a diffusion mechanism. And once we have the electric field bias, then we will have the drift mechanism. And also, we have to take into account of the generation and recombination. So we will all talk about this later when we talk about the carrier transport. There's one dedicated chapter all talk about this mechanism and the equations. And the last one is Poisson equations. So the Poisson equation is very critical. The purpose is trying to derive the electric and potential distribution based on the charge distribution. So that's a very critical. So we base on the charge distribution. So the charge distribution, that means you have some negative charge somewhere, positive charge somewhere, and based on this negative and positive charge accumulating somewhere, we are able to derive the electric and potential distribution. So these are the main spirit for the Poisson equations. So basically, once we understand these three fundamental theories, that's enough for us to face all kinds of the semiconductor device. And the first, also, when we talk about the materials, we have to also understand that there are the different types of the solids here. So there are mainly three types of the solids. One is amorphous, and one is a polycrystalline, and the last one is a single crystal. So the amorphous materials have order only with a few atoms of molecular dimension. So that's the basic definition of amorphous. And the polycrystalline material have the high degree of order over many atomic or molecular dimensions. And single crystal material has a high degree of the order or regular sum geometry periodicity. So that's a definition of the single crystal. So if you look at the schematic, this is a schematic of the amorphous, and this is schematic of the polycrystalline, and this is schematic of the single crystal. So if we look at the material of the polycrystalline, so basically we can find out that there's a certain degree of the lattice arrangement, but not in the same of the arrangement around all of the material. Only part of the material has the same degree order of the arrangement. And we can find out that in between, we often see this kind of the boundary. So in the professional term, that we call this as a grain boundaries. That's what we call the grain boundary. And of course, if you look at the single crystal, because the atoms inside this single crystal are in the same lattice arrangement. So ideally, its electrical property are superior to those of a non-single crystal material, since grain boundary tend to degrade the electrical characteristic. So usually, in the case of a polycrystalline, we have this grain boundary, and this grain boundary usually will degrade our electrical performance here. So if you are working on the ferroelectric materials, and you will definitely face the issue, because in the ferroelectric material, we have many different phases in the one piece of material. So in the end, we face the issue of the different grain size and different grain boundaries. Okay, to further understand and then to try to have the one systematic way to evaluate the lattice. So now we have to introduce the two terms. The first one is what we call the unit cell. So unit cell is a small volume of a crystal that can be used to reproduce the entire crystal. And also we have another one called the pre-material cell. So this is the smallest unit cell that can be repeated to form the lattice. And then in many cases, it's more convenient to use a unit cell than the primitive cell. So that's a typical case. So this is just a pure definition that in the crystal we have these two cell definition. And the relationship between this cell and the lattice is characterized by three vectors, which is A, B, and C. So in the case of the a very simple crystal structure, as shown here, so this is very simple crystal structure. And then so we can use these very basic vectors which to describe the any place in this inside this the lattice. So the R, which is a vector combination of A, B, and C. So I think that's pretty simple, and that's very straightforward. I think that everyone should learn this in the other more basic mathematics classes. So this is a very generalized approach to describe the relationship between the cell and lattice by using these vectors. So now we're going to introduce the several very important periodic arrangements. So the periodic arrangements altered in the crystal is called the lattice. And then we have three types of the different lattice. The first one is a simple cubic. So the simple cubic is a structure as shown here. And we can find out that we have the 8 atoms in the corner here. And then each atom actually contributes of 1/8. So then that means in this case we have 8 atoms in the corner, but each atoms in the corner contribute 1/8 to this unit cell. So in the end, the number of atoms per unit cell is equal to 1. So I think that's a very simple, the very most simple case that use a simple cubic. And another one, the middle one, is we call the body central cubic. So in the case of a body central cubic, the most important difference compared to the simple cubic is that inside the center of this unit cell we have 1 atom in the center of this unit cell, and therefore we have still the same. We have A atoms in the corner, and each one contributes 1 over A plus we have a 1 in the middle. So that means in the end we have a 2. So the number of atoms per unit cell is 2. And the last one is we call the phase centered qubit. So still very similar. We have the 8 in the corner, but now we have a 4 in the face. So we have a 1. Oh, sorry, this should be. If you look at this face, so we have a 1 in this face. If you look at this face, we have 1 in this face. So in the end, we have a 6 phase. And if we try to count the number of atoms inside this unit, which is, we have still the same, the 8 in the corner, but now we have a 6 in the face, and each one contribute to 1 over 2. So in the end, in the case of phase center qubit, the number of atoms per unit cell is 4. So that's a basic calculation to understand how many atoms consider 1 unit cell in the case of the simple qubit, body central qubit, or the phase center qubit. So this is just a similar slide that we have been described before, and now we can consider, this is the first one is a point per cell. So as we already calculate, it's a 1 point per cell in the simple qubit. But now if we try to calculate the number of density, that would be equal to this one. So that's because we only have a 1 point per cell, and then we use a 1 divided by the volume here. So that would be shown in here. Also, in the case of the body central qubit here, usually we only call this as a BCC. And then the phase center qubit, that's what we call the FCC. Here. So you can see the first one, that as I already said, this is 1 over A in the corner, and each one contribute, we have 8. And then 1 in the middle. So in the end, we got the 2. And also, in the case of ACC, we have a 1 over A in the corner and 1 over 2 in the face. So in the end, we have a 4. So if you look at more practical in the atoms that we are very often used, for example, the silicon and then the germanium. So basically, silicon is a diamond qubit structure, but now it's considered the silicon is 2 FCC sublattice constructed by the 2 FCC sublattice slightly shift along the body diagonal by the 1 over 4 cubic age. So you have a 2 FCC, and then each one is shift along the 1 over 4 of the cubic age, and then in this case, that's how the silicon atoms look like. Also, the next question is that since we start to understand the structure of the lattice, we have a BCC, we have FCC, we have a simple qubit, and it would be good allow us to have a way to indicate the phase and indicate the plane. So we will be interested in how to call this plane, how to call this plane, and how to call this plane. So that's why we have to introduce a way that we call the Miller index. So in the case of Miller index, it's basically try to have a way, a unified way that allow us to have the way to call, to indicate this plane, to indicate this plane. So the purpose of the Miller index is to describe the lattice direction and planes here. So we are interested in how to use one universal approach to indicate, to describe the lattice direction and planes here. The calculation is very simple here. So you can see if we have a plane, this is a X, Y, Z here. And if we have a plane, as shown me here, and therefore the first step is we try to calculate the intercepts in the X, Y, and Z axis. So in the intercept with the X axis is 3. The intercept with the Y axis is 2. And then the intercept with the Z axis is 1. So we have a 3, 2, 1, the first step. And the second step, we just do the reciprocal. So that means we will try to calculate of 1 over 3, 1 over 2, and 1 over 1. That's what we call the reciprocal of the intercepts here. And then we will multiply by the lowest common denominator, which is 6. So we will times 6. So this will become the 2, 3, 6 here. So now we can consider the plane in here. It's a plane we call the 2, 3, 6. So this is the step that how we can try to obtain the Miller index. So now you see it's very simple. It's just even like the elementary schools math skill is enough to calculate this Miller index. So just let me repeat again. So the first step is try to identify the intercept. And the second step is we do the reciprocal and then we times the lowest common denominator. And this is a value. This is a Miller index we are interested in. So we refer to a plane as this HKL, which is a plane for this particular plane that we are interested in. However, there are some of the exceptions that we have to consider. So these are the particular exceptions that we have to also just remind that everyone. The first one is that it is possible to have the negative intercept here. So if you look at the first case, we have this is intercept is 2, the intercept is 3, and we have intercept in the Z axis is -2. So still the same. The first step is we identify the intercept, and the second step is we start to do the reciprocal of the intercept, which will be equal to 1 over 2, 1 over 3, 1 over -2. So then we multiply by the lowest common denominator, which will be 3, 2, minus 3. But in the case of Miller index, we do not use a negative sign inside the Miller index. So in the end, we put it as a head on top of the minus negative value to indicate that there's one direction is in the negative directions here. So that's how we consider once we have a negative intercept. And also, if we are interested in the plane that has only intercept in the x and y, but however, in terms of the z direction, actually this is a plane's approach to the infinity here. So we have a 2 and 3 in the x and y directions. So now we have a 2, 3, and infinity in the one direction. So then still the same. We do the 1/2, 1/3, 1 over infinity. So then we can get the 3, 2, 0 here. So now you can realize that the purpose why we do the, so this is a plane 3, 2, 0. So once we have a 0, that means that this plane is approached to the infinite in that directions here. So now you can start to understand why we have to take into account of the reciprocal, because we want to avoid the issue of the infinite plane here. So that's another special case in the Miller index. And of course, there are some more details about the Miller index here. So as I say, that usually we use a small bracket here. That's and then once if we have the head here, that means this is a negative intercept in the one particular axis here. And if we use this kind of a bracket, so that means this represents a family of planes, which is a combination of all these planes. And if we have this bracket, that means we represent as a directions here. And if we have this bracket, that means this represents a family of the directions. So this is just some more detail that using the different brackets has some different implications here. Okay, so if you look at this example here, so we can see this is a plane of 1, 0, 0. And therefore the direction is shown in 1, 0, 0. And with this kind of bracket here. And also this is the same. This is the directions of a 1, 1, 0 of the plane 1, 1, 0. And this is a directions of 1, 1, 1 in the plane of 1, 1, 1. So the idea is very simple, just a little bit using the different variation of a bracket to indicate whether we are talking about the plane itself or we're talking about the direction of that plane. Okay, so also when we talk about the materials or the lattice structure, we definitely have to just a quick reminder that there's a different way to form the bonding between the lattice here. So you have the O10 to O10. So how do we form the bonding between the O10 and O10? There's several different possibilities, which is ionic, covalence, metallic, and van der Waals. So these are the four, 1, 2, 3, 4. Yes, these are the 4 different possible bondings that in the end can form the lattice here. So in here, we just quickly go through the text, and then most of it, you probably already learned this, because usually we have the first learning about this kind of the bonding probably is coming from the chemistry in the high school. We already learn from this, or even the very general chemistry or material science. So the ionic bonding is a type of a chemical bond that involves the electrostatic attraction between the different charges of the ions. So in a crystal, the negatively charged ions tend to be surrounded by the positive charged ions, and positive charged ions tend to be surrounded by the negatively charged ions here. So that can cause to form the lattice. So the idea is that if we have the positive charge, so definitely you will have some negative charge will try to surround this positive charge. So that's what we call the ionic bonding. And the second one is a covalent bond. So the covalent bonding results in the electrons being shared between the atoms. So that in effect, the valence energy share of each atom is full. And to be honest, the covalent bonding is the one that the most important for the most of the semiconductor material. Not all of them. Right now, we are trying to produce lots of very amazing, fancy semiconductor material. Sometimes not always have a bonding with a covalent bonding, but in the most of the case, we still consider covalent bonding. So if you look at the right hand side, this is a silicon. So we all know that the silicon has 4 valence electrons in the outer shell. So we have here, 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 here. So that's we all know. So now if you look at the next, the silicon atoms in the nearby, so we still got 4 as well. So now if we try to push these 2 silicon atoms together, so we can form the covalence bonds. In the end, we can have the 2 electrons to connect with the silicon to silicon. So that's the idea of the covalent bondings. And the next one is metallic bonding. So this is many positive metallic ions as being surrounded by a sea of negative electrons. So solely being held together by the electrostatic force. So that's a way try to understand the metal. So the idea is that inside the metal, we can still consider there's a certain ions here, but we have a bunch of the huge amount of the negative electron. Negative electron can be surrounded by the positive metallic ions here. And the last one is a van der Waals bond. So this is caused by correlation in the polarization nearby the particle. So that's the definition of the van der Waals bonds. Also, if you look the detail of our crystal solids here, in the previous slide, what we talk is always the ideal case that every solid has a perfect crystal arrangement. But in reality, we often see there's imperfections and also the impurities in the solids here. So the idea is, for example, if we have this typical lattice arrangement, but suddenly there's one place, one atom is missing, and this is sometimes we call as a vacancy. So, and also on the other hand, if we see this is a typical lattice arrangement, but suddenly there is one atom located in between the lattice side, that's we call the interstitial. So sometimes probably it's your first time to hear the vacancy, the word, but in the some of the semiconductor word we are using, probably it's your first time learn from semiconductor, but it's also very useful in the daily life communication. Just like the case of a vacancy, because the vacancy is actually more often used in our daily life communication rather than only limit in the semiconductor. In here we call the vacancy, is actually in Mandarin called 空缺. So in most of our daily communication, what we usually use a vacancy is that we try to apply the job. So you look for the job vacancy. That means that you try to ask the company whether you have any vacancy that can for your the job and the vacancy that can apply. So this is also the one example that the vacancy just means that there's an empty position, empty place, and this empty position and empty place in the semiconductor is we consider as an imperfection. But in reality, what happens if we have this vacancy? So now if you look at a crystal structure, so if we have the atoms here, but we miss one atom in one particular place. So this is we call the vacancy. So the problem for this vacancy is that since there's no atoms to occupy this place, and this empty place will be easily to have some other possible charge can flow in. For example, we can have the electrons try to fill in this place. So once you have the electron fill in this empty place, that means this empty place produce additional negative charge, right? Because ideally we don't have negative charge. The whole system ideally is in the equilibrium, is in the net charge should be equal to 0 in the whole system, because this is a case that we don't give any bias, we don't try to operate. But suddenly, because of there's a vacancy here, so you might start to face the issues that the electron charge can flow in here. And this will create the very critical and also very famous reliability issues that we call the trapping. So the trapping is also not only you will learn from the semiconductor, but that's also can be used for your daily life English communication. Sometimes I will say, I'm trapped here. What does it mean? I'm trapped here, because that means that your life being trapped. You're trapped by some like annoying things that you cannot leave. So you kind of like being fixed in a certain phase that you cannot leave. So sometimes you can say, I'm trapped here. So this is same thing. The trapping means that the charge will be certainly stay at this moment, and this charge is something that we don't want. So that's the trapping issue. But the problem is that the charge will also not stay here forever. Probably with another condition after 10 minutes, 1 hour, 10 hours, this charge can be flown away. So this is a phenomenon that we call the detrapping. So now you can see, once we have a vacancy, our whole systems become so unstable, right? Because sometimes you don't know when, but sometimes just there's an electron charge can flow in. But you also cannot estimate how long this charge will stay there. Probably after a few seconds, a few hours, this charge will flow away. But after another few hours, there's another electron will flow in. And then so the whole system becomes so unstable. So this is a kind of the unstable. As being an engineer, actually what we hope is we can try to predict everything precisely. We want to understand. We not only try to understand physics, we want to have the way to predict our device characteristic. We want to predict the electrical characteristic. But once we have these dynamics that the electron can be flow in and certainly flow away, so that is very unstable, and that creates reliability issues. So that's my point here. So vacancy or interstitial is not only just matter with there's a additional missing in the crystal, or there's a additional the atoms in the lattice in the crystal, but sometimes it also we can expect that once our material suffer the vacancy or the interstitials, in the end our electronic device always suffering lots of reliability issues. So that's why we need to find a way to solve this and improve the reliability. So this is an example how the material science in the end to correlate to our device characteristic, to correlate our electrical characteristics. And also there's another very famous one that we call the line defect. So the line defect is sometimes happen when there's an entire row of atom is missing. So for example, in this structure, you will find out that there's an entire row is missing here. So then we can consider this is a line defect. And this line defect is particularly very often happening in the case when we try to have one semiconductor put it on another semiconductor. Because if we have one semiconductor, we all know one semiconductor has one spatial lattice arrangement, spatial lattice constant between the atom and atom. But if we intentionally put another material on top the original one, then definitely another material has a different lattice arrangement, has a different lattice constant. So in the end, we always face the issue of the line defect in the interface between these two semiconductor material. So one of the famous example is in here. We can consider the bottom one is one semiconductor material, which is silicon. And then we try to have the gallium nitride, a 3,5 compound on top of silicon. Then you will find out that in most of the cases, even nowadays, lots of literature still try to discuss how to avoid this line defect between the gallium nitride and silicon. Of course, this is not the case, only limited to the gallium or silicon. Is general case in every kind of the case when we try to put the two semiconductors together. Okay, so also there's some of the additional concept related to these impurities here. The previous one, what we call is imperfection. So this is imperfections in the crystal. So it means that this crystal either original crystal already missing or has additional atom. But the impurity, it means that this is the something that coming from the additional coming from the outside, not inside the original crystal system. So the impurity atom may be located in the normal lattice site, in which case they call a substitutional, as shown here. And also the impurity can be located between the normal site, which they call as interstitial impurities. So anyhow, no matter for the imperfection and impurity, this is always a big issue for the material science. So we always try our best to reduce the imperfection and impurity as possible as we can, because in the end, this additional non-ideal effect will always cause instability of our electronic device. Okay, so although we are still in the pretty like the introduction phase, we haven't talked about the anything related to the device and then some of the current equation yet. But we already actually introduced some of the concept. Probably you might think the concept is not that critical, but actually this concept is already very useful. So this is an example that how we learn from the crystal orientation that we introduced for the Miller index, which is enough for us to understand the one particular study. In this case, this is literature related to the performance dependent of a CMOS. So we also already talked about what is CMOS. Of course, we are not talking in the detail, but at least you already know that the CMOS is a term that lots of the Earth try pay attention to. And this is a performance of a dependent CMOS on the silicon substrate orientation of the ultra thin oxide nitride, hafnium oxide gate dielectric here. So from the title, you probably can already, although you probably didn't understand what does mean the oxide nitride and hafnium oxide, that's fine, just a matter of the different gate dielectric. So sometimes there are so many different dielectric, even for me, I cannot understand everything, but at least this is just a dielectric. So we are trying to understand the performance. In here, performance is always, when we talk about the performance, most of the time, it's always related to the current. So in summary, just a paper will talk about like different silicon orientation will be impact on the performance in the CMOS. Since we talk about orientation, so we need to find a way to correlate the crystal plane. So that's why you can see inside this paper, everything is talk about this number that we talk about to indicate the crystal plane. So this is a dependent CMOS performance on silicon crystal orientation of a 100, 111, and 110. So these are the surveys inside the silicon. But how do we indicate this surveys? For sure that we use a very basic Miller index. That's enough. The Miller index is very simple but powerful that allow us to indicate the specific plan that we are interested in. So the abstract here, And then also the whole mobility, blah, 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 in the end will have a certain effect on the 110 service compared to 100. And also CMOS current will have a certain effect on 110 and 110. So that's just an example to show you that actually what we learn from the semiconductor physics textbook is everything is very, I would say it's very useful, because so far, once you know how to use the Miller index, this paper should not be difficult for you, and then you can quickly understand the most important part. But for sure, we will spend the time looking a bit detailed at how the literature is constructive and what we can learn from their writing style. Although in here I'm not talking too much in the detail of the technical discussion, but I think it will be interesting to understand how to organize the abstract and summary, and then that would be helpful for everyone in the future who need to write the English manuscript here. So as I say, the key term for the title is CMOS orientation and also the gate dielectric. So in most of the case, you don't have to be, but you can just follow this style. The first sentence of the abstract, just another rephrase of our title. So you can see in the abstract here, the first sentence, dependence of CMOS performance on silicon crystal orientation has been investigated with equilibrium gate diluted silicon less than 3 nanometer. So this sentence is exactly the same like the title, just another rephrase. Just try to say, yes, there's a substrate orientation that we consider 100, 111, and 110, and we have a certain specific dielectric which is less than 3 nanometer. But if you look at the key term, it's the same. CMOS orientation gate dielectric. So usually the first sentence for the abstract should be exactly rephrase the title, because in the end we want to have the first sentence of abstract to deliver the same message that we want to deliver in the title. But also if you look at the summary, it's the same. The first sentence summary is electron and hole mobility has been measured in a CMOS device fabricated on silicon substrate with a various crystal orientation. So now you can see the first sentence of summary also exactly the same like what we have been already described in the abstract, and also just another way to describe in the title. So in summary, in the case of the abstract or the summary part of the title part, we have to again to reinforce the key point. That's what we want to deliver. So that's why we always talking about the same things, no matter for the title, for the first sentence of abstract or first sentence summary. What we talk about are all the same things. And usually then the next part is we will start to construct our main key point for this the article here. So in the English writing, we try to identify at least 3 key points. You don't have to identify a lot, because sometimes if you try to identify a lot, usually you will confuse the readers. For the academic writing, the most important part is we try to make the complex things to be simple. We try to use the most simple way to deliver our message that our reader can understand in a very efficient way. So usually we will try to consider if every moment when you try to read or you try to write of your English, your academic article, always try to find the 3 key points here. And we use these 3 key points to expand our discussion. So you can see in this paper, the first key point is here. The first one, he tried to illustrate that there's a whole mobility enhancement in the certain orientation compared to the another orientation. So that's the first conclusion. And the second one, which is this one, the CMOS drive current is nearly symmetry on the certain orientation and without any degradation of substrate slope. So that's the second key point try to deliver in this paper. And then the third one is for the hafnium dioxide dielectric. There's around 68% enhancement on the certain orientation, and then with a certain current reduction. So that's the third point. So if you look at the abstract, so now you can see that in general, they want to try to claim that the CMOS current is highly dependent on the silicon substrate orientation. So that's the first sentence they want to illustrate. And to support this sentence, so he uses 3 key conclusions to try to provide the evidence. So the first is this conclusion, second, this conclusion, and third, this conclusion. So that's all. So that's a very typical style, try to write it in the abstract. But the interesting thing is, if we look at the summary, it's the same. Always try to illustrate the key conclusion again. So this is the first one, this is second one, is the third one here. So the first one is what they say, significant hole mobility can be improved on the certain orientation than another orientation. And the driving current on 110 have a certain characteristic. And also CMOS on 110 and 111 may not be affected by the orientation dependence of the dielectric quality. So in anyhow, what they try to deliver in the abstract is exactly the same like in the summary. So when you next time, if you want to start to write your academic paper, always trying to look at the 3 key points that to support your result. And that's already enough for the abstract and summary. And then in between, of course, we have the device fabrication, we have an experimental result, but those are just some supporting evidence that to support your conclusion, just a matter of a bunch of electrical characteristics in the end to support your statement. Okay, so this is an example of one figure showing in this paper. Now you can see what we have been already mentioned, that the small bracket actually indicate the different things, but they also mention here. So now you can see this is two kind of different brackets, 110 and it's another kind of bracket. That's for sure indicate the different meaning of the Miller index here. And then this just a matter with different mobility, different electron mobility. This is hole mobility, electron mobility, and with respect to the different crystal orientation. Okay, so last one, probably I think everyone here probably already know, but just a reminder that when we talk about the literature, or when you needed to look at the literature that you want, we always use the Google Scholar. I think that's good enough. Trying to find out the most you just type the several keywords, so you should be able to find the literature or some of the study relevant to your work. Okay, so that's the end of this chapter. In this chapter, we talk about the materials. We talk about how to form the semiconductor with considering the different junction, and we also talk about the definition of the some crystal structure and then the Miller index here. So now we will take a break for 10 minutes, and we will come back later, start to move on to the quantum mechanics.对，
就是我在 paper 上面有看到一些就是什么 donor like 的 trap。对。所以教授这边讲的是应该是 donor like， 就是说
这边的话还没有到完全的，就是这边只是 example 是 vacancy。如果是 example 进去的话，它有可能是 donor 或是satellite。对，但这边的话，当我们讲到 donor like satellite， 基本上我们考虑用 band 的方法去解释。所以这样，对，因为那个是有 band 的。就是你是导入应该是指这个 interface state， 然后你有 EC， 对 EC， 然后你会带进来这个 interface state， 所以会有 donor like acceptor like 这种东西。
其实 donor like 我能理解 ，donor like 我比较好想象，就是说你电子进去嘛，所以你这边带负电。对。所以你那个 trap
acceptor like，
对 acceptor like 是。
对，那 donor like 就是一开始是不带电的。
donor like 一开始不带电，然后电子进去之后它变带负电。
一开始不带电，然后它进去之后会，
将电子出来。
应该是它一开始是带正电，它一进去之后会不带电，它刚好是完全相反。
所以这边反而是 acceptor。
这边没有到清楚的完全的这个定义，等到我们后面讲那个 interface state 的时候，会再讲到就是所谓的 acceptor like 跟 donor like。对。
然后还有一个就是我最近在想那个mobility的东西，就是说像是这个的 paper， 对，它的通常写这种mobility通常是什么样的 mobility？ 因为
field effect
是 field effect， 对，所以因为通常 IDB 就只能求到 field effect mobility， 对，
没错，这是。
可是我看到一些 paper 是它有 modeling 出 drift mobility 跟 diffusion mobility， 那个 drift mobility 是可以算出来的，就是可以从数据得到的。
drift mobility 的话，你可能就是要考量到一块 material。drift mobility， 你要看有没有比较特别的方法。drift mobility 基本上是在讲求这个你一块 material， 然后加压，然后让它看它的整个 carry 往这边。对，所以它是两端的。对，它不是像这个 field effect 是指你有 MOSFET inversion。对。所以我不知道是不是用 Hall effect 去看。对，或两者 maybe 可以有机会去量到，不是或两者 maybe 的或。
OK， 所以通常这个 mobility 是 field effect。对。然后 drift 的话可能
因为 field effect 跟我们的元件特性最相关。 你这个 Hall effect 或是你拿到的就是 drift 或 diffusion 在真实元件操作的时候，它也不是完全靠 drift 和 diffusion。对，它真实元件操作的时候，你就考虑它是电子反转。对 ，inversion。
所以其实这种 field effect 是更实用。
对，因为这跟真实元件操作是一模一样。
OK。
对啊，因为你的 diffusion 或 drift 你都是考虑它是
一个很理想的。
对，就是说今天你的 field effect mobility 最高就是会等于你的快材里面的 mobility， 那快材 mobility 就是 diffusion 跟 drift。对，但是你永远不可能得到跟快材。
OK。
对，
好，那我知道。好，谢谢。
No, we will I will send you. It's a. Your food is it here? Yeah, you can ask him. He will join. He will join. Also join. It's a engineering report. It's a engineering display. Or display. Yeah, not your room. No. Yeah, okay. Thank you. 就是那个刚刚讲那个，就是你最后多少个 number 在 possible cell。
124。
对。
哦，就是这个意思哦。 这 没有它的 A。
Okay, we'll continue for the next chapter. So now we'll move to to the more critical part. It's close to the very unique physics that we need for our semiconductor device. So in this chapter, we will introduce quantum mechanics. So of course, we can, in terms of the, I think in this classroom that everyone comes from a different background. So if you are in the physics related background, you probably have already followed very deep quantum physics knowledge, or you probably already learned a lot of different knowledge related to the quantum mechanics. But in here, we only introduce the one that we needed for the semiconductor device. So in the end, I hope by end of this chapter, it could possibly change your typical story type impression about the difficulty of quantum mechanics, because actually the things we need for the semiconductor device is not that difficult compared that you learn from the physics related classes. So in this class, in this chapter, we will talk about the quantum mechanics. We will introduce, of course, we still need some modern physics knowledge, especially related to the wave equation. But in the end, we will introduce why we need the quantum mechanics, because we need to have the quantum mechanics to understand the very specific physics phenomena that will very often happen in the semiconductor device. So first of all, let's just use MOSFET as one example. So this is a typical structure for the MOSFET. So we have the piece of the substrate, and we have the source and drain. And this is P-type substrate. And now we all know on top of the substrate, we have the dielectric. And on top of dielectric, we have the gate metal. So in the previous lecture, we already very brief to describe the operation of the MOSFET. So during the operation, we will ground the source side, and we will start to apply the drain bias, and we will also apply the gate bias here. So in the most important characteristic, which is drain current versus gate voltage. So now we all know that the typical characteristic for the IDVG should be look like in this way. First of all, we don't have current, and beyond a certain voltage, we start to have a current here, and we define this as a threshold voltage. So the physics behind is that once we apply the gate voltage is larger enough, more than threshold voltage, then we start be able to attract enough electrons in the channel. And in the meantime, because we also bias in the drain side, so ideally this is insulator. So that means ideally the electron is not able to flow to the top, but we have the positive bias on the drain side. So the only possibility for this electron is flowing from the source to the drain and become the drain current here. And in here, what I draw is the electron flow, and then the current flow is in the opposite direction of the electron flow. So that's the idea behind that, how this IDVG characteristic come out. But what I assume during this operations, we always consider this is a perfect insulator, and we consider the perfect insulator so the electrons cannot flow to the top, even we have the gate bias. But if you try to measure the gate current versus the gate bias, if what I say is true, this is perfect insulator, your electrons cannot flow on top, even you have positive gate bias. So ideally, you will not be able to have any gate current can be sensed. The gate current cannot be measured because ideally we have a perfect insulator, and then the carriers is not possible to flow into the insulator and reach in the other side. But in reality, we always see once we apply the gate voltage, we start to see the gradual increase of gate current. And in the end, we have a huge increase of our gate current once we apply enough high gate bias here. So that means once we apply the gate bias, the carriers below the channel, below the dielectric, it's possible to cross over this insulator and reach the other side. In the end, become the gate current. So this is direction of electron flow, and then the gate current should be here. So now this cannot be understood by classical physics. So that's why we need to apply the quantum physics. We need to apply the quantum mechanics. So this is one example that how the quantum mechanics help us to understand the device physics. So let me illustrate again. Ideally, we consider this is a perfect insulator. So the basic definition of insulator is that you won't have the carrier flow insulator. So that means all the electron here is not possible to across this barrier, across this dielectric, across this insulator, and reach to the other side. So ideally, we should not have any gate current. But in reality, once we apply the gate bias, we will start to measure the gate current can be flow in the gate side here. And this is a reason that we need to apply the quantum mechanics to understand. So if we look at the conventional classical physics, so in the case of a classical physics, if we have the wall, 墙壁, if we have a wall, and then you just throw a ball against this wall, and then the only possibility can be happen is you will see the rebounds of this ball. You will see the reflection of this ball, and then you are not possible to see the ball in the other side. So if we follow the classical physics, we should have the gate current equal to 0, because you can now imagine that this is our dielectric, and then this is our electron, and then we have the electron try to flow to the right hand side and face a huge wall here. The only possibility based on the classical physics is that you can only have a rebounds, and you are not possible to have the carriers, electrons, across this wall. So if we only have the classical physics, especially the Newton physics, we should get the leakage equal to 0. But this is not true in our semiconductor case. So that's why we have to introduce the quantum mechanics, which idea is very similar. But now we don't call the wall, we call the barrier. So now if we have a barrier, the barrier can be potential barrier, the barrier can be dielectric, the barrier can be anything that shows a higher potential than the steady state. So that's what we call the barrier. But now we have the carriers. This carrier can be electron and holes. Try to inject to the right hand side. For sure, we still will see the reflection of this carrier. But based on the quantum mechanics, it is possible to have the carriers across this barrier, to across this dielectric, and reach to the other side. And then these carriers reach to the other side will become the leakage current. And this phenomenon that we have the carrier in the one side go through the barrier in the other side. This is something we call the tunneling. And this tunneling mechanism is proportional. It's highly related to our gate bias. So that means once you increase the gate bias, your tunneling phenomenon will be getting more and more obvious here. So that's why we need to understand the quantum mechanics, because the only way to understand why we have a leakage current cannot be used conventional classical physics, but can be only understood by quantum mechanics, where we have the tunneling mechanism. So that's the purpose why we have to understand the quantum mechanics. So that's why in the lots of the semiconductor textbook, in the first several chapters, always talk about the quantum mechanics, because we want to understand how the carrier can transport across to the certain barrier. Okay, so why do we need quantum physics? The idea is we want to describe the electrons movement in a micro world. So this particular case that we are facing the semiconductor is that we try to understand the electron and holes movement in the very small dimension, especially movement inside the periodic lattice structure. So if the objects are large, so usually we can apply the Newton mechanics if we consider very large objects like the general, the things in life. But so Newton mechanics works very well. But in the micro world, this is not true. The Newton mechanics doesn't work. So imagine this is our original problem. We have a piece of the semiconductor. So this is our piece of semiconductor. Now the question is that we want to understand the electrons movement inside the piece of the semiconductor. But for sure, once the electron movement in the piece of semiconductor, what actually electron face is the electron will go through the periodic structure. So this is very simple schematic of our lattice arrangement. We have the periodic structure. So now the question is, original problem is that we try to understand the electron flow inside the piece of the semiconductor material. But what electrons actually will face is the electron is actually try to flow in the region where we have the periodic structure. But now you will start to foresee sometimes this electron is very close to the atom. Sometimes this electron is far away from the atom. So that means it's actually what electron, the feeling that how this electron have is the electron is in a periodic potential, because of sometimes when electron is close to the atoms, then you have one kind of a potential. But if electron is far away from the atom, you have another kind of the potential. So in the end, the problem that we want to solve is the electron movement in the periodic potential, which sometimes electrons here, sometimes electrons here, sometimes electrons here. So that's in the end is a issue, it's a problem that we want to solve. So now we try to simplify the original problem that the electrons movement in a piece of semiconductor material become as a problem that the electron movement in the periodic potential. So this is exactly the problem that we want to solve. So in the later part, we will start to describe that how this electron movement with considering the different potential problem. So to understand the quantum mechanics, there are the three main principles. The first one is the principle of the energy quantum. And the second one is the wave-particle duality principle. And the third one is the uncertain principle. I believe most of you already learned this if you have followed the modern physics class. In here, we won't go very detailed again. We just try to describe in the later that how we're going to apply this equation to help us to understand the quantum mechanics. Also, in the modern physics, we also learn about the photoelectrical effect. So the photoelectrical effect is to demonstrate inconsistency between experimental result and then the classical theory of the light here. So according to the classical physics, if the intensity of a light is large enough, the Wall function of the material will be overcome and the electron will be emitted from the surface independent of the incident frequency. So this is a classical physics. The observed effect is that at a constant incident intensity, the maximum kinetic energy of the photon electron varies linearly with frequency. With a limited frequency, V is equal to V0, and below which there's no photon electron is produced. So the conclusion here is that the maximum kinetic energy is certainly proportional to the frequency, and only when larger than the certain frequency we start to have the kinetic energy. So this is the frequency. So this is just a reminder that what we have learned for the photoelectric effect. If you are not familiar, you can go back to check the modern physics, but it is fine. It's not that super important in the related to what we're going to discuss later. Just some the physics to understand the carriers, and also the concept of the energy quantum. So Planck already proposed this series in the 1990s, that the thermal radiation is emitted from a heated surface in the discrete packet of the energy. That's we call the quantum. So the idea of the quantum is that actually it's become the discrete energy level. So the energy of this quantum is given by E is equal to h mu, where mu is the frequency of radiation and h is a Planck constant. I think this is also the very well-known equations. And in the 1905, Einstein also interpret the photoelectric result by suggesting that energy in a light wave is also contained in the discrete particle bundle. The particle-like packet of energy is called the photon. Whose energy is also given by E is equal to h mu. So the photoelectric effect explains how the discrete nature of a photon and demonstrate the party-like behavior of photon. And this is just a very famous equation. You probably already learned this. And the phi is the minimum energy or work function and required to move the electron from the surface. So that's some background introduction about the first proposal of the concept related to the energy quantum. And also, as you already know, that there is a series, what we call the wave-particle duality. So that means the photons can both act as a wave and particle. But how about the electrons here? So Compton effect, the particle-like behavior of electromagnetic. So in the 1924, the boy proposed the existence of a matter wave. So he suggests that since wave exhibits a particle-like behavior, particles should be expected to show the wave-like property. So this hypothesis of the boy was the existence of the wave-particle duality. So here is some famous equation. The momentum of photon can be expressed here, and because we have a wave-particle duality, so the wave-particle can be also expressed by this. And also the last one, just a quickly review, is the uncertainty principle. This is also proposed in the by the Heisenberg uncertainty principle proposed by 1927. Also applies primarily to the very small particle and states that we cannot describe with absolute accuracy of behavior of these subatomic particles. So the uncertainty principle describes a fundamental relation between the variable, including the position, momentum, or energy, and time here. So based on the uncertainty principle, we can have the delta P times delta X larger than H bar, and also the delta E times delta T larger than H bar. Okay, so that's a basic review for the all fundamental knowledge here. But to be honest, we only if you forget all this fundamental knowledge, I think it's fine as long as you remember that there's something happen. If you are interested in, you can look at that in the detail. But I would say to understand the quantum mechanics in semiconductor, it's more simple to understand the uncertain principle, to understand the wave-particle duality, to understand the energy quantum. So in here we will don't go detail, but we will start to move on to the, for me, is more interesting and more easier part. So as I say, the question now is we want to understand the electron movement. And now our question is that we want to understand the electron movement in the periodic structure as shown in here. And actually it's become the question of the electron movement inside the periodic potential. So if you look at this schematic of all three kinds of electrons can be in here, electron can be here, and the electron can be here. So we can divide the three scenarios. The first one is electrons in the free space. So that's the first case. And also possible, the second case is electron in the very deep potential well. That's the second case. Or third case is the electron is in the shallow potential well. So basically we are trying to understand all three cases, and then these all three cases are the possible happen during our semiconductor device operation. So the first one, we'll start from the most simple one, the electrons in the free space. So in the case of electron in free space, actually we can consider our potential here, Ux is equal to 0. If our potential here is equal to 0, that means the electrons is movement inside the free space. So this is the first case that we will discuss. Okay, so the next one is the second one here. We consider the electrons inside the infinite potential well. So in this case, we consider this is an infinite potential well. That means so we have the place of x equal to 0 and x equal to a, and then we consider the potential well as shown here. And since this is our carriers inside the potential well as shown here, so the electron movement in this region, but now we can divide by 3 regions. One is the region 1, region 2, and region 3. And because now we consider the infinite potential well, so that means the region 1 should have the infinite potential, and also the region 3 should have the potential approach to the infinite. So that's the case of the second one. We consider carriers movements inside the infinite potential well. Okay, so the third one is also very simple. The third one is the one we point out here. So what we really consider is once the electron face the state potential function. So now we consider we have the state potential function like this one, and now we only the state potential function has a potential of a V, and now we have the region 1 and region 2, and we try to understand the electrons movement in the case with the state potential function. So these are the 3 cases that the can represent all the possibilities that once electrons moving in the periodic potential. So if we can try to understand and derive equation, then basically we can understand how the electron movement inside the periodic potential. And that's the goal. Still have the, sorry, has the fourth one. Still have the fourth one. So the fourth one is a combination of the previous three, which is we have the potential barrier. Because in this case, actually, the electron here not only face a step, it can be the electron here moving to this potential barrier and reach to the other side. So this can be also happen. So this is the more realistic potential barrier that we will have to take into account. So we have the potential barriers in the specific region. In the place of x equal to 0 and x equal to a here. And then we can still divide by region 1, region 2, and region 3 here. But now this potential, this is potential here. The barrier has a potential V0 here. So what we try to consider is that the electrons move toward this potential barrier and with energy smaller than V0, and what will be happen. So this is the fourth cases, which is the most important one, because this is pretty realistic to the case that what we'll face in the real semiconductor device. So this is exactly the case for our MOSFET, where we have shown we have a source and drain. We have the dielectric. We have the metal, gate metal here. So what we have been shown before is that once we apply the VG here, we have the electrons, formation electron in the channel. And now if you look at in the position of the electron, what reality of this electron phase is exactly the same case here. This electron face a potential barrier, and therefore we have to understand how this carriers behavior once face a potential barrier. And of course now we know the conclusion. Conclusion is there's a chance electrons will appear on the region 3, but why and how? This is something that we need to spend the time to understand how this electron is able to tunnel and reach to the region 3. So this is exactly the case that we will face very often, over and over again when we analyze the semiconductor device. Okay, So once we finish the motivations, now if we continue to move on to understand this phenomena, now is a time with a little bit boring that we need to introduce some equation. This equation is very powerful, help us to understand the previous 4 cases here. But still trying to keep in mind that the equation is not going to confuse us. The equation is always just try to help us to support our speculation. So now we have speculation. Right now, even for me, of course, I know the answer. You probably also know the answer that the electron can tunnel through the barrier. But this is just our speculation. How we can prove it, that's why we need to apply this equation, apply the boundary condition, and solve it. And then once we have this analytical equation to support us, that truly proves that our speculation is correct. So here I will introduce the time-independent Schrödinger equation. So the first equation, this is very well known Schrödinger equation. I think everyone who a little bit in the engineering field should already hear about this, even you don't understand clearly before, but it's fine. It's just an equation, just don't have to feel like it's so scary. Although this equation looks scary, but of course, for being the engineer, we always try our best to simplify the question. So this is a one-dimensional non-relative Schrödinger's wave equation. So we have an equation shown here, and most important part is this one, the phi xt, where phi xt is a wave equation, and also we have the Vx is a potential function. So these are the 2 most critical functions that we are interested in. And first one, we assume that wave function can be written in the form of this one. So in this case, where small phi t is a function of position x only, and the phi t is a function of the time only. And why we can do that? Because we use separation variable, this kind of math. I think many of you, when you learn the engineering mathematics, sometimes get confused why we have to learn this, because sometimes I feel the engineering mathematics is like a dictionary. It's so many things inside, but due to the limit time, it's difficult to explain why you have to learn in the very small, for the every different method you will learn in the engineering mathematics. But this is one example that we apply the engineering mathematics here. So by using the separation variable method, so we can start to assume the wave function can be the 2 function which is only the x position only, and also the time only. So that's the first step. And then once we put this one back to this equation, so then we can have this formula here, and with a further calculation we can become here. Also, we can consider our phi t is equal to here, which will be in the end equal to exponential minus j omega t. Then the wave equation here can be simplified as shown in here, which is equal to E. So finally, we have the equation. The second derivative of phi x plus two n h r squared e minus vx phi x equal to 0. So with several techniques, we try to derived from the original equation to here. But now, what will be the most important implication from the top equation to the bottom one? So the top one is the equation whether you have the location and time dependency. But now, from this one, we only have the location dependency. So that means this is a time independent equation. So that's our purpose. As I say, as being an engineer, we always try to find a way to simplify the question. So now we try to eliminate the inference from the time. We want to only discuss the location dependency, because if you look at the this case, the only parameter from this schematic as shown here, the only parameter we expect that will influence our carrier's movement, which is location, x-axis, and there's no time inside. So that's why we want to, in the end, to simplify the equation to become the time-independent wave equation. And the wave equation has the physical meaning. Actually, the wave equation is to describe the behavior of an electron in crystal. So also from the previous slide, we already know the wave equation can be considered as an equation where we have a phi x times phi t, and will become the phi x exponential minus j e minus h bar t, which is equal to this one. So now we do the small trick. We try to multiply this wave equation twice, which will be equal to this times this phi star. And then we all know once we increase, put the star here, that means this equation now is become the exponential positive j e over h bar t. So now we try to multiply these two, and then that means this and this can be cancelled. So in the end, we can have this equation come out. So also this equation indicates that the phi x squared here. So now again, we're doing the similar things. We try to eliminate the influence of time. We want to have the equation only the location dependent. We want to have the equation that are time independent. So this equation indicates the probability density function and is independent of the time, and it's only dependent on the location. So that's the very important conclusion, and especially in here, not only have the independent of time, another very important implication is the probability density function. Okay, so the implication here is not only the time independent, but also the implication of the probability. Okay, I hope it will work. So here not only indicate that this is time independent, but also indicate that this is a probability density function. So what it means, a probability density function? It means that actually once we consider the electron movements, we also have to consider the interesting point related to the probability. So that means once we have this barrier here, so we have the electrons try to move from the left hand side, and then we all know that in the end we will finally try to derive something related to the tunneling. So in the end, the electrons have the chance to tunnel through to the right hand side. And then the conclusion based on the wave equation tells us that the electrons tunnel through in the right hand side. This mechanism is correlated with the probability. And also location dependent only. So this probability indicates that once the carrier moves to the other side, we cannot precisely know everything. That the only thing we can know is the probability. So that's why this is a probability density function and it is independent of the time. And this is also pretty fit well that we have already talked about the uncertainty principle. So that means once a carrier tunneling in this region, we cannot determine everything precisely. What we can only know is that how high the chance can be here. What we can only know is about the probability. So that's the physical meaning of the wave equation. Okay, so the short summary of the wave equation. In the 1926, Schrödinger provided a formula called the wave mechanics here. So this is a combination of the three different series that we have already discussed. In the end, we come out with this equation, and then the most important conclusion is this one. So in the end, we can understand that the wave function is a probability density function and is independent of time. And the one major difference between classical and quantum mechanics is that in classical mechanics, the position of a particle or body can be determined precisely. So that's the classical mechanics. But however, in the quantum mechanics, the position of a particle is found in terms of a probability. So that means we cannot determine precisely. So that's a major difference. One of the, not all of them, but that's one of the difference between the classical mechanics and then the quantum mechanics. So now we get to step by step to a little bit approach to all the carrier phenomenon in the semiconductor device you will face. So now the most important is that you understand that the particle cannot predict precisely, can be only estimated by consider the probability. So in the later part, when we talk about the carrier concentration and so on, how high a concentration can be, how do we estimate the carrier concentration, we will introduce using the probability density function to describe the carrier's concentration. And then the reason at that moment we have to use the probability density function is because of here we can only determine the carrier probability based on the quantum mechanics. To further move on to address the case we described before, we have 4 cases, right? So the first one is we introduce the wave equation, and second one is we need to start to provide the boundary condition, because the boundary condition can help us to have a more precise calculation later. So since this represents the probability density function, so that means the integration minus infinite to the positive infinite of this dx is equal to 1, right? Because of the overall probability in the end, it will be equal to the 100%, which will be equal to 1. And the wave function and its first derivative must follow the property of the total energy and potential Vs are finite everywhere. So that means must be finite, single value, and continuous. And also this one must be finite, single value, and continuous. So here is some of the examples that to illustrate that the potential function and corresponding wave solution. So the first one, the potential function is finite everywhere. The wave function as well as its first derivative is continuous. And also the second one is potential function is infinite for the case where x equal to 0 and then the x larger than a. And also the wave function is continuous at the boundary. And then the first derivative is discontinuous. So these are the information related to the boundary condition. So finally, we have enough background information and then the mathematical knowledge. Now we will start to try to apply the wave equation to the case that we have been already described before. The first case is an electron in the free space. So in the free space, that means the E and Vx is constant. And then also approach to the 0. This is V. So that's the free space. So once we have this assumption, what we can do here is this will be approach to 0, and therefore our wave equation here can be simplified to this case. And based on the engineering mathematics, we all know we can assume the solution for this equation is this one. Phi x is equal to a exponential jkx plus b exponential minus jkx, and k is equal to this one. And the time dependent of the solution is here, which in the end our phi x xt is equal to phi x phi t, and which will become to this one exponential minus j omega t here, and this is phi x is here. So now with this equation, finally we have this one can be derived, and this one is actually very straightforward, can be understood very easily, because the A represent the wave traveling in the positive x direction. So the A is the wave traveling in the positive x direction, which is this one. And also the B is a wave traveling in the minus x direction. So in the end, based on the derived equation, I think it's pretty fitting for the understanding of physics, because this is a free space. So this is free space. That means your carrier can be only travel in the positive x or in the negative x, right? And also now we have the equation here to support our speculation. So that means that our understanding in the free space is correct, because this is free space. So then there's only the chance to travel to the right and then also travel to the left. So this is the first application that we use a wave equation to understand the electron traveling in the free space. Okay, I think I will stop here because I think I need to try a little bit why this sometimes connection works, sometimes didn't work. So we will stop here and then we will see each other in next week. Also a reminder that I just uploaded the homework yesterday, so please submit your homework in next week's class. Okay, so see you everyone next week.